This is the third video in the FOA series about networks. We've talked about what is a network and how network architectures connect users. Now let's talk about how they share bandwidth. The basic network architecture of most networks is a star network, or as we keep saying, it's more like a tree and branch when you add multiple levels of connections. But this type of network does well at connecting users so that any user can talk to any other user in the network. So we can connect all of the users in a network, shown in the triangle on the right, to servers, the triangle on the bottom, and storage, the triangle on the top, and then to the internet, the triangle on the right. But the question is, how do we make those connections? And how do we allocate the bandwidth so that the users who need to transfer large amounts of data are accommodated as well as those who only need to transmit a small amount? A star network, which most of our networks are today, is very similar to the phone system that's been around for more than a century. The phones, going back to the old analog lines, required a direct physical or electrical connection between the two users who were talking to each other. So in the early days, the phones were switched originally by operators literally plugging connectors into switchboards, and later on using electronic switching with originally tubes and then solid-state circuits. When the phone system was converted to digital transmission, there was still a need to ensure that two users who were talking over the phone system had a continual connection. So a new system was added called time division multiplexing. Basically, the backbone, which operated at 1.544 megabits per second, could accommodate up to 24 voice circuits that only required 64,000 bits per second. So each connected phone conversation was assigned a time slot on the backbone circuit. And so the transmission would be time slots 1 through 24, and then repeat 1 through 24, and repeat 1 through 24. So each of the connected users had a real full-time connection to the person they were talking to. This was combined with the switching, the physical switching, to create what was called time, space, time switching. When Ethernet was introduced, it offered a quite different problem. All of the connected users were physically and electrically connected to the same cable. So they all had to have some way of accessing and transmitting data on that cable, the bus, or as Ethernet's developers called it, the ether. That's where the name Ethernet came from. So they developed an access scheme that's one of the great tongue twisters of all times, CSMA/CD, which stands for Carrier Sense Multiple Access with Collision Detection. A connected user on an Ethernet bus would listen to see if anyone else is transmitting. If no one was transmitting, they would start transmitting, but would continue listening themselves. If someone had started transmitting at approximately the same time, so there were collisions on the cable, both users would back off, wait a random amount of time, and start transmitting again. It's a system that works without directly connecting any of the users, but it has a problem, of course, that the more users you have, the higher your likelihood of collisions and the less efficient the network is. When Ethernet went from a coaxial cable bus to unshielded twisted pair cable and a central hub, the hub basically acted as a repeater. So if anybody transmitted through the hub, their signals were sent to everybody else, and you had exactly the same problem you had with a single cable with everybody physically connected. You would have collisions. You would still have to use the same CSMA/CD protocol. The users would back off, wait a random amount of time, and try again. But you had the same problem in that the more users you had, the more likelihood you had of collision, and the less the efficiency of the network. One way to guarantee access to the network is by a token. Basically, a token is sent out on the network to each user in turn. If they're in a ring, the token merely gets passed around the ring until it reaches a user who wants to send data. If they want to send data, they attach the token to their data and send it out with the address of where it's going. When the data is delivered, the token is released and goes to the next user. This creates what's known as a deterministic network. In other words, any user on the network can always have access to the network, which is important if you need, for example, a way to create an alarm on the network. As networks became bigger and faster, another solution was needed. But fortunately, electronics became faster and more powerful and cheaper, and so switches replaced hubs. Instead of taking an input from a user and repeating it to all other users, a switch would look at an input, decode the address, and forward it to the port which it is addressed to. Switches typically have 20 to 40 ports and can switch duplex. So a single user can be sending data to one user and receiving data from the other simultaneously to provide full duplex transmission. This, of course, means that the system is much more efficient, but it requires that switches provide buffering. So, for example, if it's trying to transmit data to a user from two different users, it has to switch one into the other, and that requires internal buffering. But switches are basically what's used in almost every network today that's based on star-type architecture. A smarter switch, sometimes called a router, is used to create a mesh network. Basically, routers are higher level switches that can switch data between multiple networks. They have multiple connections to create these mesh networks. They can learn various routes or be programmed to send data along routes to ensure that it's going to be able to get where it's going. It can avoid busy sections by simply taking an alternate pathway. Both the phone system, which use programmed switches with fixed routing, and the internet, which uses routers with the ability to learn what routes are possible, both are used to create mesh networks. Passive optical networks, like those used in fiber to the home and passive optical LANs, use a much more sophisticated system. Part of the switching is done optically by the splitter in the network. The splitter splits the signal going downstream to multiple ONTs, which can in turn connect many users, and combines this optical signal coming upstream into one port on the OLT. The OLT uses time division multiplexing to steer data to the appropriate ONT or user and to handle upstream combination of signals from the various users. It uses some very sophisticated switching, which was necessary because these systems often had large numbers of users, thousands or tens of thousands in fiber to the home. So it does what's called dynamic bandwidth allocation, to dynamically allocate bandwidth where it's needed and create an extremely efficient network. That's just an overview of how networks share bandwidth. The biggest point we'd like to make is that one cannot simply calculate the available bandwidth of any connected user on a network. Some people take a simplistic viewpoint and divide network speed, say 1 gigabit per second, by the number of users, say 100, to get a quote average bandwidth of 10 megabits per second. The fallacy of that assumption is that all users are using the same amount of bandwidth, which they don't. One must consider networks statistically and consider the demands of the users, allowing high traffic users to take what they need and still allow low traffic users access. Newer switches and optical LAN OLTs are smart enough to steer bandwidth where it's needed. This is one of a series of lectures on networks done by the Fiber Optic Association, the Professional Society of Fiber Optics. You can find more information about networks, fiber, and even copper and wireless on our online guide. Go to the FOA homepage at thefoa.org and you'll find links to the FOA online guide.